Yeah, it's fine. Did it start? Yeah, it started. Good, okay. Anyway, so I'll be posting videos of the lecture so that if there's something that you missed, if you miss a lecture, if you just can't show up for whatever reason, you can always go and watch the YouTube version of it, okay? Don't make it, a routine that you skip class, but if you gotta be out for any reason, no need to contact me, just watch the YouTube video of the lecture. Of course, on Thursdays, you just make sure you get your homework quiz done, okay? All right, are there any questions? Okay, here we go. So first and foremost, let's get a definition of math down, because that's what we're gonna be doing. So, and this is, what I'm gonna do is, especially initially, is be kind of rigorous, but not mathematically intensely rigorous. This is not a math course, this is a physics math course. But I do wanna show you a little bit more of the backbone of math than maybe what you see when you see it introduced in a physics context. So we're gonna start with the idea of definitions. And whenever I write up a definition, I will begin it with a green box of sorts. And the green really means go, okay? Because with a definition, there is nothing to prove. With a definition, you're just given something, and you can take that as true and go and find and discover other things that are based on that, okay? So definitions are not something that we need to prove. Theorems, on the other hand, and if I ever write a theorem up, I usually put a red bracket. Oh man, my red marker's dying. The red bracket means, nope, stop, we've got to prove this, okay? You can't just take this as true, you've got to prove it, okay? Now we are by no means going to prove everything, but we are going to prove a few things, especially at the beginning, just to kind of get proof writing under your belt. And this is really not mathematical proof writing, this is more physics proof writing. Okay? So there's a sense in which green means go ahead, red means stop, and prove me. All right? Now when we're doing proofs, often we see the term if and only if, which is often just if with two F's, okay? Where the if here is essentially the equality that whatever you're ifing is necessary, okay? And the only if part of this is the statement that whatever you're dealing with is sufficient. So we have necessary and sufficient. So let's consider the following. A if B, and what this implies is that if B is true, then A, okay? Or what we can say is A if, or only if, whoa. In which case, A implies B, and then of course we have A if and only if B, oops, which of course then implies both, okay? Does everyone feel comfortable with this set of ideas? Or do you need examples, or? I will do a proof later on today where we'll have if and only if. So we'll go both ways. Are we good? You guys are a talkative lot. I wish you'd shut up. You're driving me nuts. I'm trying to talk over you, and you're always, okay, I'm just kidding. Okay, one page of notes done. Last time I taught this course, I had one student, he railed on me. He was like, you always went like 10 minutes over, and I had to go to work, and if you went over, I couldn't eat before I went to work. And I was like, I'm sorry. Okay, I won't go over it again. So I'm going to end at 6:15 on the nose. All right, what are vectors? Let me find the right space to write this, and this marker has already got me a bit down. Vectors. Who can provide me with a quality of vectors? Like, just give me something that you can do with vectors. Yes?
A magnitude, and it has a magnitude and a direction.
A magnitude and a direction. Okay. with vectors? What are vectors? Just anything. Throw it out. Chances are you won't be wrong.
They're additive.
Additive, yeah, you can add vectors. What else? Oh, come on, folks. Have you never worked with a vector?
You can multiply them. Into
You can multiply them. Yeah, you can multiply them. Just so you know, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 things on my list. What else can you do with a vector?
rotate it.
You can rotate it, yeah. Anything else?
Translate it.
Sorry, say again?
Translate it.
Translate it, okay. I'm going to stop writing you cans on everything. Okay, anything else?
Does transformations count?
Well, rotation is an example of a transformation, so. Nothing else? Are they things with multiple components? What do you think? Can you multiply them by a scalar? Yeah. What about, can't you represent them as column matrices? Aren't vectors just column matrices? Yeah, they're column matrices. What about things that you can expand in an orthonormal basis? What do you think? Yeah? No? Possibly? Yeah, you can expand them in an orthonormal basis, where that's normalized. And we got to do 10 because translation was not part of my list. So there's one more thing on my list. You can multiple components, direction and magnitude, multiply to get scalars, multiply to get. Oh, you can multiply them to get for scalars or vectors, right? Dot product, cross product. Okay, so there we go. So there's now 9 things. All right. It's going to turn out that in our fundamental definition of vectors, most of this is not true. Very little of it is true. We can add to the fundamentally defined vectors more structure, okay? But the fundamental definition of vectors does not include most of this. And I'll strike off what is not included, okay? But let's get a formal definition of vectors. So here we go. Our first formal definition of vectors. A group is a system of elements G and an operation of composition, which I'll just call the dot. The dot can mean many different things, so don't immediately go, oh, dot multiplied. No, don't think about that. It's just a generic operation that consists of a set G with a single operation, and this is what I just said, single operation, that satisfies the following, okay? 1, dot is closed. That is, for A and B on, everybody familiar with this symbol?
G.
For any element A and B on the group G, so G is a set, And I'm just picking two pieces of it. They can be the same piece if you want, but I'm picking two of them. If I pick any two, I'll do an IE here. Then A dot B, and again, I'm saying dot, but I don't necessarily mean dot product. That's just crap, okay? A dot B is equal to C, and C must be on G. So this is closure. It just says if I take two elements of the group and I combine them, the result must also be an element of the group. Okay? Now let me ask you a silly question. Do you think the dot product can be this operation? I'm talking about the regular dot product. What do you get if you dot two vectors together? Do you get a vector? No, you get a scalar. But that's okay, don't worry, I mean, that's not even close. Okay? All right, so 2 dot is associative. And I must say, like, most of these definitions are in terms of the dot, because otherwise you just got a set. You don't really you don't have a lot of rules about, here's a set. So it's combining things with this dot. That's where the structure of the group definition comes from. You should talk to somebody at some point about how this is going to go, at any rate. So for the associativity, what we have is that for A, B, and C on G, then A dot B dot C is the same as A dot B dotted with C. Okay? That's probably what you're familiar with from your algebra class. I don't remember what year you learned that kind of stuff, but that's associativity. There exists an identity which we will call E in general. Sometimes it's the number 1, sometimes it's the letter I, sometimes it's a diagonal matrix with nothing but ones along the diagonal. It could be different things. We're going to call it E in general. There exists an identity E on G such that for all A on G, for any element on G, I did a Physics 100 studio this morning, and there were 130 students in the room, and some girl, like halfway across the room, raised her hand. She's like, "Could you speak up?" I started yelling at them, and I don't think my volume has turned down, so I'm sorry if I sound like I'm yelling. If you can't hear me, though, raise your hand, let me know. For all A on G, A dot E equals E dot A equals A. That's exactly what you expect from the identity. If you combine the identity with anything, you just get back the thing you combine the identity with. For every A on G, there exists an A inverse on G such that A dot A inverse equals A inverse dot A, which is the identity, E. Okay? This is a definition. And I want you to notice, I have not said anything about vectors. I want to give you a definition of vectors, but we got to give you some other definitions first, starting with a group. Okay? Now you'll notice there is no thing that says that A dot B is equal to B dot A. What would this property be called if it contained this? It's what we call an abelian group, but it's the property of commutivity. Okay? That's the old word for it. If I can reverse the order and get the same thing, then it's commutative. Okay? We call this in the group context abelian. And abelian can be a feature of a group, but it doesn't have to be. Okay? Obviously, abelian groups are a bit simpler to work with. But it's not a requirement that the elements compose in an abelian fashion. Okay. Are you ready? You ready for it? Okay, here we go. So, a field, I'm not there yet. A field is a system composed of elements F with two operations, plus and dot, that satisfies one, the subsystem F plus is an abelian group with the identity being 0. Okay? 2, if we let F prime be all x on F except x equals 0, then the subsystem F prime with the dot operation is an abelian group with an identity which does not have to be 0. It certainly isn't 0 because 0 is not included, but it's going to be something. We'll just call it E prime. Okay? And then for property 3, for A, B, and C as elements of F, we have that A dot B plus C is A dot B plus A dot C. That is, the dot is distributive with respect to the plus. Okay? Notice I'm not saying the plus is distributed with respect to the dot. All right, so this is the definition of a field. Now let me give you examples of groups and fields just so that we can make sure we're comfortable with these ideas. A group. So for example, if I take the real numbers with plus as the operation, then those form a group. What's the identity? 0, exactly. If I take a number and I add 0 to it, I get the number back. That's the identity, okay? If I take the reals with multiplication, so the dot is a multiplication of numbers. What's the identity in this case? 1, okay? So see, the identity can change its nature, all right, depending on the context. What about if I take matrices with matrix multiplication? What is the identity? So if I take 3 by 3 matrices and I use matrix multiplication, what's the identity in that case? It's the identity. Yeah, it's the identity matrix. It's the matrix, its diagonals are just 1s. Everything else is 0. Okay? Can anyone give me an example of a field? So I need a set of elements, and I need an operation plus that satisfies this, and I need an operation dot that satisfies this. Can anyone give me an example? Okay, if you were in 2nd grade, and I asked you, give me a set of stuff that you can add and multiply, what would you say? The real numbers, yeah, the real numbers with plus and multiplication. Yeah, that forms a field. Okay, so does the complex numbers. Okay. There are other fields, but these are the 2 fields that we're most often going to encounter. Okay? What's important is that when you're defining a group, there's only one operation. You might be tempted to say, oh, I can add matrices as well as multiply them. But in terms of the group as it's defined, there's only one operation. So if we're using matrices and we're just multiplying them, don't go about adding them, okay? The field is defined with two operations and with this really strict set of conditions, okay? So a field is way more than just taking a group and adding in another operation, okay? So fields are very, very specifically defined. Groups are way more generally defined. All right, I know you guys are sick and tired of waiting, so here we go. And I'm not shitting with you this time. Although I do have to figure out where I'm going to write this. I'll try and fit it in down here. Okay. A vector space over a field F is the set of vectors V satisfying the following two conditions, only two. V with the addition operator, okay, forms an abelian group with the identity being 0. And 2, for every alpha on the field and x on the vector space, okay? So we have vectors, and then we have the elements of the field over which the vector space is defined. These are really just numbers, okay? They're never going to get more complicated than just being numbers, but I'm going to call them a field to be technical. For every number and vector, okay? We should satisfy the following. Alpha beta x equals alpha beta x, where alpha and beta, so alpha and beta are elements of the field, and x and y are elements of the vector space. B, alpha times x plus y is alpha x plus alpha y. C, 1 times x is equal to x. And D, alpha plus beta times x is alpha x plus beta x. Okay? This is our definition of a vector space. All right. Now, I've given you this formal definition, but we should actually just ask, give me some examples of vector spaces so that I can see the power of this formal definition versus just my intuition about vectors, because we all have intuition about vectors. All right? So let's look at a few examples of vector spaces, and running out of room. I'm just going to have to erase these. Okay. Examples. An n-tuple of real numbers okay, over f equals the reals. Whoops. Okay. addition between vectors being defined as, well, let's take one vector. That's the elements of x, and then let's add to it the elements of y. And this is, okay? This has n elements, this has n elements, this has n elements. You can immediately see the closure of the group. Okay? If I add two vectors together, I get a vector. Okay. And if I take an element of the field, which is just the real numbers, so if alpha is an element of the real numbers, then this is alpha times beta 1, beta 2, which is just alpha beta 1, alpha beta 2, okay? All right? And then E equals 0, which in this case is 0, 0, dot, 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 0. Okay? We will call this space Fn equals Rn. So we're talking about an n-dimensional vector space, and we might as well just call it Rn, because everything in this vector space is real. Okay. Now, this should be the most intuitive, the most familiar example of a vector space that any of you have ever seen. This is the vector space you encountered the first time you encountered vector spaces in calculus, and certainly the first time you encountered them in physics. Two-dimensional vectors, three-dimensional vectors, they're just these things with as many components as you have basis vectors, and then you can multiply them by scalars, da 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 da. Okay, that's basically what this is encoding. So what else can we get out of this definition of vectors? Well, first of all, if we take n equals 1 in the above, oh wow. If we take n equals 1 in the above, the vector space itself is the real numbers. And it's over the field of real numbers with plus and numerical multiplication being the operations. Okay. Numbers can form a vector. Yes, numbers can form a vector space. Okay. 3. An n-tuple of complex numbers over the field of complex numbers with the same conditions as in example 1. Okay? We'll call this Cn. Okay? And then, just like 2 from 1, for n equals 1, V equals C over F equals C. So the complex numbers themselves form a vector space. It's a one-dimensional vector space, but it's a vector space. Okay? Now I know what y'all are thinking. I knew there was a one-dimensional vector space. This is all just crap. Let's look at a more interesting example. the set of all polynomials to order n. Okay? That are functions of a real variable. Oh my gosh, my pen is dying. Oh, sorry. We'll call the real variable t with real coefficients. So the vector space in this case is what we'll often call Pn over f equals r. Okay? And then of course we can generalize this. The set of all polys to order n that are functions of a real variable, notice it's real, t, with complex coefficients. We call this Pn over the field f equals c. Okay? So let's look a little bit closer at these last two examples, because these are maybe not as obvious. All right? So for x on Pn, so we'll do 5 and 6 together. For x on Pn, x is got to be equal to, first of all, there's a constant. Okay? And then we have a number from the field, and it can be the reals or the complex, depending on which of 5 or 6 you're using, plus alpha 1 times t, plus alpha 2 times t squared, plus dot dot dot, plus alpha n t n. Okay? Now I have a question. Is Tn an element of this? Is Tn an element of this set, of the x on Pn, where the x's take this form? Let's take the alphas to be elements of the reals, just for simplicity. Is Tn an element of this set? What do we need to have happen for this thing to be Tn? We need this to be?
0, 0, 1.
Is that allowed? Yeah. 0 is on the reals, and 1's on the reals. Okay? T squared plus Tn minus 1. Okay? So this is a large set of polynomials. It's not that everything has to be non-zero. Okay? Things can be 0. You just can't go higher than n. Okay? Now, I show in the notes, and I'm not going to go through it because I don't want to run out of time, that this satisfies, with addition, the properties of an abelian group. If you think about it, without even writing anything down, some of that should make sense. For example, if I take 2 of these polynomials and I add them together, do I get another polynomial of degree n or smaller? Yes, I do. Okay? Addition is the operation we're talking about. We're talking about this right here. Okay? Addition is obviously associative. What's the identity? It's 0, yeah. If I take a polynomial and I add 0 to it, I get the polynomial. What about inverses? What's the inverse of this, where I'm picking alpha 0, alpha 1, alpha 2, alpha n? What's the inverse? The operation is addition.
Negative.
Exactly. You take negative alpha naught, negative alpha 1, etc. You add those two things together, you get the identity, which is 0. Make sense? Okay, I'm not going to go through the details of that. All right. You can also show that these conditions are satisfied as well. Okay? And I've got this written up in my lecture notes, but I'm not going to write it down because it's really just going to be writing this down with very specific entries from here. Okay, so I'm not going to do that to you, but it's in my notes. All right? But what I want to now do is go back to this list because we've got a definition of vectors. What on this list is required in the definition of a vector space versus optional structure you can add on to it? How about magnitude and direction? Is that required? Nope. What about the addition of vectors? Yes. What about you can multiply them for scalars or vectors? Nope. At no point in this definition do we multiply vectors. Rotating. It's not part of the definition. Translating? Nope. 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 Multiply components or multiple components. Do vectors have to have multiple components? No. Remember? This guy and this guy? Or sorry, this guy and this guy. The real numbers, the complex numbers, those just have one component, but they form a vector space. So nope. Can you multiply it by a scalar? Yes. You can multiply it by a scalar. Do they have to be represented by column matrices? Nope. This vector space, its elements are polynomials. Certainly not something you put in a column matrix. And can you expand it in an orthonormal basis? No. How do you define orthonormality? That's based on the product of two vectors. That's not in the definition of vectors. We will introduce these ideas, but what I'm trying to get at is what is in the fundamental definition of a vector space. And then we'll add structure to it. Okay? So are there any questions about this thus far? Now, clearly, many of you already see where some of this can go, right? Because obviously this is super useful when you want to talk about space or space-time, because vectors, is representing them as, intiples with coefficients, all that stuff, that really applies in this sort of classical mechanics scenario. Whereas functions as vectors, well, that obviously plays a role in quantum mechanics. Okay? We will eventually learn, just a few lectures down the road, that everything in this story can be represented by matrices, even the functions. Okay? So there is something special about the matrix story. It is not saying that these things are matrices, but rather they can be represented by matrices. Okay? All right. So, let me see, 3 more. We got this. All right. So now, we want to, again, sticking with just the definition, nothing more. Let's see what we can talk about. Oh. So, obviously, something that you should be familiar with from your handling of vectors is that to describe them, a basis is a really useful tool. Okay? A basis in a vector space is actually a property of a vector space by definition. However, notice I'm not saying an orthonormal basis. The word orthonormal comes from defining the product of vectors, which we will do. Okay? But that product is not a part of the definition. So what I want to talk about is a basis of the vector space without any dependence on an inner product or orthonormality. Okay? So let's see what we can do. Oh man. Okay, I'll start writing in blue. Blue is the new black. But green and red are still going to play their roles. You're not going to know what green and red are, but you will after you talk to somebody. All right. A basis in a vector space V is a set xi on V of linearly independent vectors that spans the space, i.e., any element of V is a linear combination of elements in the basis. Okay? And this gets green because once again, this is a definition. It's not a theorem. There's nothing to prove. Okay? Green means definition, red means theorem. Green means go, red means stop, and prove me. Notice this definition, well, it only relies on the sum, okay? To see that, we'll say a set, well, actually, okay, so there are two properties here. There's linear independence and there's spanning the space, and I'm going to treat those individually, and then by demanding both of them, we'll come back to a full basis. So linear independence can be defined as follows. A set of vectors, of n vectors, should be careful, is linearly independent if and only if, and of course we know we can write that as if the sum from I equals 1 to n of alpha I times xi, remember alpha i's are just elements of the field, so for us they're usually going to be numbers. The xi's are the elements of the vector space. If the sum over alpha I xi equals 0 and the set xi are linearly independent, then this means that alpha I equals 0 for all I. Okay? I'm going to draw some pictures to just make this clear. So if we're in three-dimensional Euclidean space, okay? Imagine if I take the vector x1 and I take the vector x2, okay? Are those linearly independent? Well, let ask you, so if I say, if I want to sum from 1 to 2, alpha I, xi, and get 0, the only way I can do that is if the alpha i's are 0. Because if you think about it, you could take x1 and find the component of it which is parallel to x2, and maybe if this is big enough, it'll cancel x2, but you'll still have the perpendicular component of x1. So there's, and I'm saying, like, this angle is fixed, and as long as that angle is not 0 or 180, if it is, you know, but as long as it's not 0 or 180, then these are linearly independent. Because in order to add them with coefficients to get 0, the coefficients have to be 0. Does this make sense? Okay. What about those 3 vectors which are coplanar? So they all sit in a plane. That plane is in R3, but they sit in a plane. Are these vectors linearly independent? No, they're not. Okay? Because you can sum these vectors with coefficients and get 0 with the coefficients not being 0. You know, you just pick -1 for x3, and then that might symmetrize this, and then you add it up, you get 0. I mean, it just kind of depends on exactly what I drew, but at any rate, hopefully it's obvious to you that if you're given 3 vectors in a plane, then they're not linearly independent. Because you can, by multiplying them by coefficients and adding them together, get 0 without those coefficients being 0. So I just want to stress, this is the definition of linear independence that I'm using right now. I'll give you another one in just a minute that is probably more familiar to you. Okay? And then last but not least, we're in R3, so we can actually take a non-coplanar x3 Are these linearly independent? Yes, they are. Okay? Because once again, in this case, in order to get the sum of the 3 vectors to be 0, I need all the coefficients to be 0. Okay? I mean, this might not be obvious, but remember, you could take the component of this, which is in the plane defined by x1 and x2, okay? And then you can demand that these 3 add to 0, but you're still going to have the orthogonal component of x3, which the only way to get that thing to add to 0 is to make that coefficient 0. Okay. Well, let's try another one. For P3, the vector space composed of polynomials of degrees 3 or less, consider x1 of t is t minus t cubed, x2 of t is 2 plus t squared, x3 of t is minus 1 plus t, x4 of t is minus 2 plus 2t cubed. Is that linearly independent or not? It is? How do you know? Sorry, say it again?
Only x2 has t squared in it.
Only x2 has t squared in it? So why does that make it linearly independent?
Because you can't cancel out the t
me make sure. Oh, you can't cancel out the t squared. Okay, I agree with you. But I can take a linear combination of these and set that coefficient to 0. Okay? In fact, what you'll discover is that alpha 1 is minus 2, alpha 2 is 0, alpha 3 is 2, and alpha 4 is minus 1. Then the sum of alpha I xi is 0. But notice, not all of the alphas are 0. A linearly independent set says if you have the sum being 0, all of the coefficients must be 0. Here is a counterexample. The sum is 0, but some of the coefficients are not 0. Okay, so I just, I'm trying to give you a definition that you can use. You can also use your intuition. I mean, you were trying to rely on your intuition, which, will help you most of the time, but in occasion it will fail. All right? Any questions about this? Okay. All right. Now, we can take this and we can put it in a more familiar form. Oh yeah, that was a definition. This is an alternate definition. Well, actually, it's the definition of linear independence. But what we can do is we can take that definition. I'll just remind you, a definition requires no proof, okay? And then from this definition, we can form the following criteria. The set of non-zero vectors xi is linearly independent if some xi, where 2 is less than or equal to I, is less than or equal to n, is a linear combination of the preceding ones. Okay? This is a different way to, in a sense, define linear independence, but this is not a definition. This is the definition. This is actually a theorem, something that can be proved from this. But this is more intuitive, okay? Remember, if a vector can be written as the linear combination of other vectors, then that full set of vectors, the ones you're adding together and the one you get, are not linearly independent. Hopefully you remember that from like algebra, where you say, oh, the number of equations is equal to the number of unknowns, therefore, well, there is the condition of linear independence, right? You know what I'm saying? Okay? Well, now is the time. Yes?
Does that say dependent or not a linear combination? I feel like that's the opposite.
The set of non-zero vectors is linearly, oh, sorry, you're right, it's dependent. Thank you. All right, so we're going to prove this one. One of the few proofs we'll do. And it's an if, so I got to prove it in both directions. Okay? So bear with me, this is going to hurt a little bit. Hopefully not that bad. So let's first do the if, the necessary. Okay. Suppose that we start with only one vector. Okay? if I choose one vector, does that constitute a linearly independent set? One non-zero vector, and I should specify. Is that a linearly independent set? Yes. I mean, after all, well, this is just alpha 1 x1. For this to be 0, if the vector's not 0, what does alpha have to be?
0.
It has to be 0, okay? So one vector is always linearly independent. It's silly, okay? Now, what we can consider is more than one vector, sets of more than one vector, and ask whether that set is linearly independent. And then the way we'll approach this is we'll say, okay, if you give me 4 vectors and ask, are 4 vectors linearly independent? Then what I can do is I can look at a subset of them and ask if that subset is linearly independent. And if it is, then I can use that in the proof of whether the full set is linearly independent or not, okay? Now we can regress this all the way back to a subset of one vector, because that vector is always linearly independent, okay? So that's the basis for the following argument. There must be a smallest number k for which we transition from a linearly independent set to a linearly dependent set. Okay? I mean, just to give you a simple example, you know, if I'm in 3 dimensions and I have 4 vectors ain't ever going to be linearly independent in 3 dimensions. It's not going to happen. If you start with 3 of them, then those 3 might be. Okay? So in that case, k is essentially 4. It's the number where we move from being linearly independent to a linearly dependent set. All right? Now, okay, so what this implies is that up to k minus 1, the sum from I equals 1 to k minus 1, alpha I, xi equaling 0 means that all of the alpha i's are 0. Okay? Are we on board with that? I'm saying the subgroup is linearly independent. So the group from I equals 1 up to k minus 1, and then the kth term is what's going to break that. Okay? So going up to k minus 1, we have the linear independence condition satisfied. All right? But if we do the sum from 1 to k, and that sum equals 0, then this implies that alpha I does not equal 0. That some alpha I in there, or maybe multiples, some of them are not 0. Okay? But this means that alpha k itself doesn't equal 0. Otherwise, we would have that sum from I equals 1 to k minus 1 of alpha I xi equals 0 implies that alpha I does not equal 0. Okay? But this is a violation of it being linearly independent. Okay? So if alpha k does not equal 0, if alpha k does not equal 0, what can you do with it? What can't you do with 0?
Scale.
Huh?
Scale.
Well, you can scale by 0,
Oh.
but that's close. What can't you do by 0? Divide. You can't divide by 0, okay? But that's okay, because alpha k is not 0. So what we can do is we can write xk is minus 1 over alpha k times the sum from I equals 1 to k minus 1 of alpha I xi. That is, the kth vector must be a linear combination of the others. All right? Now what we've done is we've done the if part of this, because what we did is we said, okay, this group is going to be linearly dependent, and let's show that that means that the kth vector is a linear combination of the other vectors. Now we've got to do the only if part. That is, we have to start with the assumption that the kth vector is a linear combination and prove that that implies that the full set satisfies the linear independence condition, or linear dependence condition. Okay, so only if will be so let's start with xk equals sum I equals 1 to k minus 1 alpha I xi. Okay? We're starting with the assumption that this vector can be written as a linear combination of the others. That's where we're going to start, and now what we're going to do is use that to prove this. We want to go the other way. Okay? So start with this, and we'll set alpha k equal to minus 1. Then this becomes sum I equals 1 to k alpha I xi equals sum I equals 1 to k minus 1 alpha I xi plus alpha k xk, where this, of course, is now just minus xk. Okay? And we're going to set that to 0. All right? Then, if we set alpha k plus 1 equal to alpha k plus 2 equals dot 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 equals alpha n equals 0, we have that the sum from I equals 1 to n of alpha I xi equals 0 with sum of the alpha I not 0. Okay?
All right. Are there any questions about this? Yes?
Should that be K minus 1, K minus 2 instead of,
K,
or is K just in the middle?
no, K's in the middle, so we're going, so the linearly independent set is alpha 1 dot 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 alpha K minus 1. Okay? And then alpha K is our special case, and then there could be more. Okay, this has to go over the entire space. All right? All right, but hopefully you all realize this is the condition of linear independence. Or sorry, of linear dependence. All right. Now, very quickly, I'm going to let you go in 1 minute. A basis in a vector space is a set of vectors which are linearly independent, and now hopefully you're somewhat comfortable with finding whether a set of vectors is linearly independent or not. This is the defining condition. This is a related condition. Either one of these can be used, okay? That spans the space, all right? Now, I'm not going to get technical with you. I can, and in the notes, I do get a little bit technical, but I just want to go the quick and easy route. To span the space, how many vectors do you need? As many as the dimensionality of the vector space. Okay? In fact, this is how we define the dimensionality of a vector space. The number of vectors in a complete set or a basis is the dimensionality of the vector space. In many cases, the dimensionality of a vector space is kind of obvious, like R3, oh, it's three-dimensional. When you start getting into functions and so forth, it can get a little weirder. Okay? I do have some more notes written up on spanning, but I'm not going to go over them. I think they're very straightforward, so you can look them up online. Are there any questions before we disband?
So are all of your notes on Canvas, or is it eventually due to class or on Canvas?
So I am going to post these
Okay.
onto my webpage, which is linked from Canvas. I mean, honestly, you should bookmark my webpage and not go to Canvas every time, because the only thing I'm going to do in Canvas is give you your grades
Okay.
and your homework quizzes. Your homework quizzes will appear in Canvas, okay?
Okay.
I used to have everything handed in, and then I only did my course website, but anyway. So just go to my course website. But that's where you'll find the lecture notes, okay, which is a bit more detailed than what I've written up here, and the videos. Okay, the videos are going to be on YouTube, but I'll have them all linked from my course website. And if you're really interested, you can look at the videos from the last year that I taught this, which is going to be a slightly different set of topics. Yes?
Are the homework quizzes no longer in class?
Right, so the homework quizzes are no longer going to be in class. They're going to be opened up at 8 a.m. on the day of the quiz, and they're going to close at 5, and you get them through Canvas, and you'll have a 20-minute window. You start whenever you want, but once you start, you'll have 20 minutes to submit,
Okay.
okay? I want to get as much class time as I can, because last year I kind of went, I couldn't get through all the topics, okay? And that's, honestly, part of that is because I would give a quiz, it was a little on the hard side. We ended up in the quiz for like 30 to 40 minutes. That would eat up a lot of class, so I don't want to do that. Yeah. So just 20 minutes, and you pick it and you do it before 5 p.m. Somebody else have, yeah.
Do we have to scan those in, or do
You can take a picture, and you can scan it if you got a scanner, or you can just take a picture and put it in. And the instructions will be there, and we'll talk more about it before next Thursday. We'll talk about it next Tuesday, because next Thursday. But yeah, so there'll be 2 questions. You can do them both, and then whichever one gets a higher grade, that'll be your grade for that homework quiz. Okay? Or you could just do one, and if you get that one perfect, you'll get a perfect score on the homework quiz. The whole point of this is to keep you from cheating, to make you digest the material. Instead of just handing in a homework and then forgetting about it, no, I want you to go back, do the homework, and then process it, think about it, so that you can use it. I'm doing 2 questions and I'm ignoring 1 because if you were handing in your homework and there were 5 questions on the homework and you did not get 1 of them done, you could get 80%, right? 5 questions, you get 4, miss 1. Well, if I asked you 1 homework quiz question and it was on the 1 homework question you didn't do, that would be unfair. So that's why I'm asking you 2 totally unrelated ones, and I'm only grading the best 1. That's the reason I'm doing that. Hopefully that makes sense.
We can still do them both, right?
You can do them both, and we'll grade both, and we'll give you the grade on the higher of the 2.
Okay.
I'm not going to add the grades together. I'm just going to give you the grade on the higher of the 2.
Would it be possible to open it at 7 instead of 8?
Sure. Yeah, I can open it up. Yeah. I mean, does anybody want it any earlier than 7? Okay, yeah. I'll open them at 7. Send me an email reminding me of that then.
Okay.
Right, any other questions? Okay, yeah, so earlier on I mentioned I had brain cancer. I do have brain cancer, and there is always possibility that I could end up in the hospital. So I got a scan last Friday, and I'm going to find out the results of it next Monday. So I'm here and I'm fine, and you know, it's all good. But you'll find me a little. I might be searching for words that I can't figure out. I used to not be that way, but I am that way now. So anyway, don't worry about it. But I just want to let you know because it could impact things later on. I don't know. We'll see. Okay? All right. See you guys Thursday.